Hi there. So we're going to go work through a simple RSA example here. A small number example. This is not secure, but it's basically going to give you an idea of how this all would work. And so again, I have my stuff on the left-hand side here. I do want to remind you, just kind of in no uncertain terms, do not use just any calculator or spreadsheet. Okay, it's really important because if you do, well, I mentioned in previous videos, what's going to happen is you're going to end up approximating values, and this is all going to, it's not going to work, is the bottom line. So you want to make sure you're not using something like that. So Wolfram Alpha, again, works pretty well. I mean, heck, you can even have it on your phone or something like that. So it's pretty straightforward. So I picked a simpler message here. Okay, go. So we're only looking at two numbers. It's this might be something you would send secretly to somebody, like, okay, go ahead with your plan. It's your go, or something like that. So we don't really need a longer message to get the idea here. Okay. Put them in plain text numbers, so just using the alphabet like we did with the previous message. And then what we're going to do is we're going to pick two prime numbers. So here's where our example is definitely a much smaller number example, because the idea is that when you're actually doing this to keep things secure, you're going to pick really, really large prime numbers. That's why, the larger the prime number, in some respects, is better. So our example is pretty small, so that's pretty straightforward. It's worth mentioning, I'm going to go ahead and just kind of, whoops, no, I don't want to do that. What I want to do is I want to highlight this. So this is, I'm just going to like red that, because I don't want, these are numbers that are secret. We don't want people to know. That's the whole point of RSA, is this public key encryption. There are certain things that we're going to hold on to, and then there's certain things that we make public for other people. Okay, so the first thing that we do is we know what our primes are. Okay, no one else does. We take those two numbers and we multiply them together, and we get this n value. N is actually part of the public information, so we'll make that green. Okay, so that's something that we can give away to somebody else. Okay, because we're using Euler's theorem here, we do need to calculate phi. So since a phi of the number n. So this essentially what n is doing for us. N is going to be our mod. So that's what we're going to be using. So we calculate phi. So here's where these prime numbers come in handy, because we know that 2867 is based on two prime numbers. Calculating phi is just a matter of multiplying one less than each of those primes together. Since n is not going to be calculated with any other number of prime numbers, it's always going to be two numbers, and it's always going to be one less than the primes that we've chosen that we're multiplying together. So 46 times 60. Now we are going to hold on to our phi value as well. Okay, that's part of no one else needs to know that. Okay. The next thing we're going to do is we're going to pick a number that is our public key. Okay. So 7 is our key, our public key. And the only thing that we need to make sure about 7 is that it is relatively prime to phi. So it doesn't. I picked 7 because 7's a prime number. It's a small number, so that's totally fine. But it doesn't have to be 7. Okay, I could have picked 143 would have worked, because it's 143 is not a prime number. It's 11 times 13, but that is also relatively prime to 2,760, so it would work out. Okay, that's really this part is the only thing we need to work. Whoops, I keep doing that. We only need to make sure that that's relatively prime. That is also part of the public information. Okay, and then the last but not least is we need the decrypt. So, and just like we did before, I'm going to take my key, which is what I'm going to be raising things to as a power, and I'm going to take the inverse of that, mod phi. So everybody else has the 7. That's something I've done, but they don't know the phi value. Okay, Now, granted, if they knew 2867, this fairly, probably not too hard, could be broken down by brute force. And we could find the primes. And once we have that, basically we have no secrets anymore. So keep that in mind. This is definitely too small to keep secrets. But anyway, so we pick this, and just like we did before, we can do 7 to the -1, and we're going to mod that 2760, and we get, when it eventually gets there, there's our 1183. Okay, so pretty straightforward. So what are we going to do? So, and D is part of our keep that close to our vest. So I'm going to read that too. So this is a good way to kind of keep track of this. The primes, the phi, and the decrypt value are all the things that we hold close, we keep private. The stuff that's green, the N value, the product of the two primes, and the public key that I'm offering. This is what you give to somebody else. Okay. So how do we then calculate the cipher number? Well, the N is our modulus, and the 7 is the exponent. So I'm going to come over here, and so I'm going to take my OK, which is 1511. So 1511, I'm going to raise that to the 7th power, mod 2867. Go ahead and enter, wait for Wolfram Alpha to do its thing, and it comes back with, eventually, my computer's slow, 291. So there's my ciphertext, okay? And then I can do the same thing for 715, so I go ahead and replace that with 715, hit enter, wait for it to calculate, 92, okay? So there we go, and so somebody would use, you would basically give them that information. You'd give them the mod, you'd give them the exponent, and then they can take these values and encrypt them and send them to you. But without this 1183, which they can't find 1183 without knowing 2760, which they can't really figure out very easily without knowing what the primes were to begin with, we can then decode it. So how do we decode it? Well, just like before, and I would strongly encourage you to check the decryption anyways, even if you're like, oh, I'm sure I did everything right. So if I come over here and I do 291 raised to the 1183, so there's my decrypt, but I'm still in mod 2867. So remember, the only time we used the phi to calculate as a mod was to calculate the decrypt key. So I hit this enter, and if all goes well, we should get our 1511 back again, and there it is. And then just to make sure, let's plug in 92. Hit enter. And if all goes well, 715, what do we get? 715. Okay. And that's basically how RSA works. The security of the system is predicated on the idea that if you pick sufficiently large enough prime numbers, there's no way, it would take an extremely long time to factor the product of those prime numbers into the primes. And when we talk about large prime numbers, I'm not talking about 3-digit prime numbers. I'm not talking about 10-digit prime numbers. I'm talking like 100-digit prime numbers. Okay, this is not something that is easily factored by brute force. So that's one of the reasons that RSA works for us. So what this does is it allows us to send out, like, hey, here's the way to send me a secret message. You give people that information, but they have no way to reverse engineer where you came up with that. That's what this is all about. Okay, so the stuff that you hold is the two primes, the phi of the product of those, and the decrypt code, which is based on phi, okay, and your key. And then you give them what essentially is the mod, which is the product of the two primes, and you give them this. Okay? If you have more questions, let me know, but that is essentially what RSA is, and that's what we've been leading to this whole term.